Hello. We're going to write a contest. Byte. Not ByteRace. It's called just Codeforces round 956. I'm a bit hungry, so I'll eat a bit. But what can I do? So everything is working, yeah. Well, let me prepare a bit more. Camera is working, yeah. Okay, I guess it's fine. So 1 minute till the start of the contest. We still need to eat. Okay, let's go. Let's go. Let's go. Let's go. Array divisibility. Ah, okay. Not very hard. So, what do we need to do? We need to go down from n to 1 and satisfy the requirements. So find done should return a VI. Sorry, it's probably from the previous contest. So we say VI VN. And we go down from n to 1. So what do we do here? Positive non-zero integers, yeah. So we try to find the sum of all numbers which are divisible by k. So we start with k minus 1. And we say that S is sum of S and... Okay, let's just say that it is S plus Vj percent k. And now we just say that v k minus 1 is simply k minus s. Basically, that's it. One, two, three. What? It's that simple. We just put all numbers from 1 to n. It's so stupid. Oh my god, this is a very stupid problem. Okay, did I manage to solve it? No. I didn't read this number. Yeah, this is incredibly bad. Actually, this is incredibly bad. Okay, problem B, I think. Okay, basically this operation does not change the sum modulo 3 in any row and in any column. So so yeah, so basically we just need to check all sums in all rows and all columns. Ah, I should read them as if they're strings. So Aij is Sj minus 0. Okay, find ans A, B. And I need to return a bool. So it returns a bool. And we need to check all columns and all rows. Okay, and if SA is not SP, ans is false. Then the same thing about B, about columns. Okay. Yes, 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 no, yes, no, yes. Perfect. But I'm very slow, unfortunately. So I already spent 9 minutes on these problems. Yeah, not very good. Problem C. Have your cake and eat it too. Okay, this is 3 pointers. This is the 3 pointers problem. And we just do it with 3 pointers. And then read 3 arrays. Do I need to print yes? I need to... What do I need to print? I need to print starting and ending indices. Okay. So, okay, let's make struct ans. Okay, so if like ans dot a dot x is -1, for example, we print -1. Else we need to print 6 numbers. Then B and B, then C and C. Okay. Let's write this function find ans. And what does it do? It seems like there is some sort of thunder outside. Not exactly easy. Let me think. Okay, fine. Let's do something. So let's say that we have 3 pieces, A, B, and C. Let's store their sums. Should the sums be long? Yeah, probably yes. Okay, and also we want to store let's find their total sum. And let's say that A is taught initially. So what? Let's perform, like, I don't know, 6n iterations. So also I want to store the borders. So the points where some piece ends and another piece starts. So let's say that everything starts at 0. Okay, so what do I want to do? I want to actually take so first of all, if A is at least third over 3. Let's also say LL minimum is third plus 2 over 3. So if A is at least minimum and B is at least minimum and C is at least minimum, then I need to return that we won. So so we need to find out these segments. So A starts at point SA and ends at point S. Is this array circular? I'm an idiot. I'm an idiot. Oh my god. Is this not circular? Yeah, I'm total. I'm a trash. No, everything of that is not needed. So instead of that, what I needed to do was consider all possible permutations. So let's find first our prefix sums. Let me think. Okay. So check ans supposes that the order is correct. Okay, so let's do everything here. So let's go. So A is the first one. Oh no. It's not what I should do. No, it's not what I should do. I also need... Oh my god. Okay, let's do it, but here we will need to fix the sans. So for example, here we will need to swap B and C. Here we need to swap A and B. Here we need to swap so here it's tricky. So I actually have answers for B, then C, then A. So I need to swap last two, so now it's BAC, and then A and B. Oh my god. Okay, here I have answers for C and B, so firstly I need to swap C and A. So now it's BAC. Yes. Finally CBA. Here I need to swap A and C. Okay, the same thing for SC. Okay. Now we want to find the value of B. So if B is at least mn, or we return the answer. So A is from 0 to SA minus 1. B is from SA to SC minus 1. And finally C is from SC to N minus 1. One one two four five five. 1 1 2 4 5 5. Yes, probably. 5 6 1 2 3 4. Probably yes. Minus 1 minus 1. 1 1 3 3 2 2. Okay. Minus 1 1 2 3 4 5 7 3 4 6 1 1 2 3. Okay, I am lazy. Let the system check it instead of me. Well, 9 minutes and I spent 26 minutes instead. Still not very much, probably. Well, it's because I didn't manage to read the statement correctly. And also, it's not obvious how to implement such a problem. Swap dilemma. Given two arrays of distinct positive integers a and b of length n, we would like to make both arrays the same. Yes, now in one move we can choose some index L and R in A and swap AL and AR. Okay, this is a very standard problem. So first of all, it's just about the parity. It's just about the parity of some permutations. Let's go. Okay, so first of all, we need to write a function which sorts and finds number of inversions. What does it do? It runs inversions. First of all, it says vi b equals a, finds its size, and returns inversions recursive of a, b, 0, n. What does it do? So first of all, if L is at least R minus 1, it just returns 0. Otherwise, it says int M is L plus R over 2. Then it sorts 2 halves. Then it proceeds with the merge part. So I is L, J is M, and for int K from L to R. So what do? We either take the left element or the right element. How do we choose between left and right? So if AI is less or equal than BJ, then we want to take the left element. But before that, we need to check that I is less than M or J is at least R. Okay, in this case, we can take the left element. So we say that, no, not A and B, A. We put it here, we say that B K is AI plus plus, else BK is A J plus plus. And then we need to copy and return sum. But before that, we also need to check the number of inversions. So how do we find number of inversions? If the element that we take is from the left part, it does not add up on the number of inversions, but if it is on the right part, then actually it adds so sum, we say that it is sum plus equals what? So this element aj is to the right of all elements from I to m. So probably something like this. So okay, here we go. So inv1 is so inversions rec of A. Inv2 is inversions rec of B. Now if A is not equal to B, then return false. Also, now let's check if there are some equal elements. So if AI minus 1 is AI, then return true. And finally, we need to check the parity. Not inversions rec, but just inversions. Return inv 1% 2 equals inv 2% 2. Yes, no, yes, no, no, no. Probably it's fine. So actually, this function should have been in my template from the beginning. From the very beginning, it should have been in my template. Unfortunately, it's not there. Okay, let's remove it. Let's go on. Problem E. I love balls. Alice and Bob playing the game. And balls are out of which K are special. Hmm. Okay, it's very clear what's what we need to do in this problem. It's very clear. Actually, Okay, so what? TKN or what then? V and first K are special. Okay, so first of all, let's find the sum of all interesting numbers, interesting balls, and not interesting balls. So special and not special. Special is sum of special AI modular m. And not special is also the same thing, but starting with k and less than n. Great. Now, so we need to understand what are the parts. So if there are k special balls, not special. So there are n minus k not special balls. So how many of them does the first player take? So he or she takes n minus k plus 1 over 2 not special balls. So the first player takes this many not special balls. Yeah? So we need to multiply n minus nsp by this number and divide it by n minus k. Unfortunately, n minus k might be 0. So instead of that, we need to use an if. Okay, what about y? Y is the same, but without plus 1 here. Okay, what about not special? For not special, actually we need to add 1 to both these numbers. Therefore, here we write plus 2, and here plus 1. No. And here plus 1, yes. And it returns. Instead, let's just put 11 here. Not everything is fine here, unfortunately. Ah, well, here I need to use special numbers instead of not special. But still something's off. 15, 15? What? Ah, here I need to say that it's sum of unclud text and this product. No, again, something's wrong. I think for some parities it is wrong, and for some parities it is right. Yeah, because when k and n are of different parities, I actually like the answer. But when they are of same parity, I kinda not like it. Ah, no, actually here the parity is different and the answer is wrong. Hmm. I don't understand why is that happening. So we have k special numbers and n minus k not special numbers. So first of all, we somehow put a permutation of not special numbers. So they are not special. And since there are n minus k of them, yeah, since there are n minus k of them, we have that like n minus k over 2 ceiling goes to the first player, and n minus k over 2 floor goes to the second player. Then actually all these k special numbers, they independently go in one of these gaps. Each of them goes in one of these gaps. And there are n minus k plus 1 of these gaps. So again, this many go to the first player and this many to the second player. But with plus 1 in the... I think it should be plus 3 and plus 2, not as I have written. Yes? No. For some reason I don't understand why it doesn't work. Well, all numbers where the answer is wrong are very huge. Okay, here, the fourth. Also, it seems a bit swapped. It seems like it is a bit swapped. But why does it seem swapped? Like, I don't understand who is the first one and who is the second one. Okay, again, the first k balls are special. So I take the first k balls and put them in the special sum. Then I take the other balls and put them in non-special sum. Firstly, I take the non-special balls and I understand that half of them goes to the first player, half to the second player. It's really weird. Okay, let's ourselves make some easy tests. Yeah, so for example, 1, 1, 1, 5. Okay. And if it's 0, then still it's 5. Okay. Now let's take like 4 and 12. No, 4 and 12 here, but for example, 2 balls and none of them are special. Then expected is that both take 8. If 1, yeah, then 14 and 2. And if both are special, then it's 16, 0. Yes. I don't understand why it's swapping something. Why is it swapping something? Maybe I need to put it like this. However, I don't know why is it the case. But possibly, no. Maybe here I need to write like this. Again, I don't know why. Ah, maybe my modulus is wrong. What is my... Ah! Wait, what? Oh no. My modulus is wrong. But I have already used this modulus, didn't I? Haven't I? Okay, probably not. Oh, this is a disaster, to be honest. Okay. It's a bit of shame, but... Oh my god. So I solved in 61 minutes problem E, whereas it took 29 minutes for Turumax. Yeah. Yeah. Great. Not exactly fast. Problem F. So we have an array, we have its subarray, and we value it as a minimum XOR of two different values of this subarray. We want to find the kth smallest value over all subarrays of length at least 2. Well, actually, it's some sort of a binary search. Or what? Okay, first of all, is it true that if there is some minimum value of this thing, then it is unique? Actually, no, it's not unique. minimum value of AI XOR AJ. Okay. So the answer to this problem is some 32-bit number. Let's consider this bit. Yeah? So let's consider this bit. So the question is, can it be 1? And actually it can only be 1 in some 2-element arrays, because if there are at least 3 elements, then there are at least 2 elements in which the first bit is same. And since it's the same in the XOR, this value will be 0. Okay? So basically, we have it that the first bit of the answer is easy to find. Can we find the rest of the indices? For example, the rest of the bits. For example, assume that we already know these bits. Yeah, for example, 0, 0, 1, 1, 0, 1. What can we say about this bit? I don't know. Probably. So problem F is actually too hard for me. Maybe we can switch to problem G instead. Wow. Actually, this user was faster than Rainbow in this problem. Oh no, this is awful. This is awful. Yes, it's awful. Okay, so basically what are they saying in this problem? They're saying that I want, so we have a path. I want to find the sum of the following XORs. This XOR 0, this XOR 1, this XOR 2, etc. This XOR something, and then these XORs. So how can it be done? Yeah, so firstly, let's just find the sum on this path. Okay? After that, I would like to fix it. I'd like to fix it. And how can I fix it? Fix this. Well, to fix that, I need... let's iterate over the number of bits. 0th bit, first bit, second bit, etc. And for each bit, I just need to fix it somehow. How can I fix it? For example, let's assume that I am fixing bit k. In this case, I need to consider this path to the root, and here I need to fix everything. I need to somehow find the alternating sum of some interesting. It is actually interesting. So we need to find some subfunction which is nice to find. So let's. What do I want to say? I want to say that. What we would like to do. Okay. First of all, there's a problem is I have some vertical path, I have some chosen bit k, and I have some number. And I want to find the number that it changes if I some number a, for example. So here I write a, here I write a plus 1, a plus 2, etc. a plus t. Then I end it with kth bit. And I want to find out how it changes if I XOR with these numbers. How the sum changes if I XOR with these numbers. So this is the question. To answer that question, first of all, I need to find this sum for the root path and subtract the same path, the same sum for this path. So this is reduced to two root paths. So now this is the root. Okay, this is the root. Okay, what next? Next, actually, let's assume that a equals 0. So if a equals 0, how to solve this problem if we can do it for a equals 0? If we can do it when a equals 0, then it's kinda easy. So if here this bit is 1, okay, let's assume that this bit is 1. Then I need to find some piece of path where it's still 1. Then it becomes 0. And I just apply here this function. And how I do this? Basically, I have something like the number of ones on a path, something like this. Okay, and the number of ones on some vertical path. So I need to store it. What about the case when this bit is 0? When this bit is 0, I again apply a lot of ones. Find the total number of ones. And then I need to subtract the case when a is added 2 to the power k, and now it's also kind of easy. Well, it's pain. It's a lot of pain, but at least I understand how to solve it. And since I understand how to solve it, let's do it. Mm-hmm. So the number of nodes, then the values, then the number of queries, then the queries themselves. Then we need to find the answer for A and R, and we need to print it. So what? We also need the graph itself, I guess. Yeah. So we start with. So actually, we need to construct a structure. So let's say tree TAE. Then we need to answer some queries. Ans.pushback tree.find ans on R and return ans. Great. And also we need to construct the tree. Okay. So for PIF from E, we say that gf.x.pushback f.y yx. Then we need to make some parents for each vertex to find its parent, and it can be done via DFS. So for each vertex we want to know its depth, and we want the array of jumps. We want the array of binary jumps. Okay, so what? So what? So what? So what? So what? So let's run a DFS. What does it do? It says actually let's fill it with -1s or with infinities, actually better. So if depth of 2 is greater than depth of v, this means that actually we never visited this vertex in our DFS. So Ju will contain parents, initial parents. So here we say that jump 0, 2 is v, depth of 2 is depth of v plus 1, and we run DFS of 2. So now we need to construct. Okay, actually we can construct jump array here. So int maximal jump is 1, and while maximal jump is less than n, we need to continue making our jump array. So what do we do? We say that jump dot push back jump dot back, and iterate over all vertices, and we say that jump dot this is what? Is we need to take this and then jump from it. Yeah. Okay, we have filled the binary jump thing. Are we able to find ans now? Probably still not really. what do we need to do then? Okay, first of all, we need to find the LCA. And it's a common unpleasant procedure. Okay, so if depth of x is greater than depth of y, is at least this plus this. And then we say that x is jump jx. And if dy is at least dx plus this, then y is replaced. Then if x is equal to y, then we return x. And otherwise, we again do this. And if jump x is not jump y, we say x is jump jx and y is jump jy. Else, and in the end we say return jump 0x. Okay, this is LCA. Now let's find it here. Oh, okay. So what do we need to do? We need to actually to do what? Find bamboo answer from x of length let me think. So actually I want to write here the number of vertices that I want. How many vertices do I want? Something like dx minus dl plus 1. Then ans2 is find bamboo ans from. Also, I want to write here 1 because the answer increases from bottom to top. Here I want y to dy minus dl, but this time minus 1. And now ll ans is ans1 plus ans2, and I return ans. Okay, so now we need to find bamboo ans. Int x, int how many, and int increment. Great. Actually, this is also a difference of two bamboo answers. It's a find root ans of x dx plus 1 and C. Also, I also want the initial number, actually. I want the initial number. Yes? Yes. So in. So the initial number here is 0, and the initial number here is the length of the path. Like, dx plus dy minus 2 times dl. This is the initial number. So this is incremental, this is in the initial number. Okay, I find rootants from x, this, c, and in. And also I find uns from up of. Okay, instead of this, I would probably like to. Okay, I can. Okay, so if dx is greater than h, then actually I want to find then I need to go up from x by this number of vertices. Then I need to actually I don't need this number, I guess. Then I need to say that it is c plus h times in. And then I return uns. Okay, let's write the function up. It's kind of basic. So if h contains this, then I say that x is jump jx and return x. Okay, now we need to find rootants. Actually, in is the initial number, so it should have been like this. Okay, so now we have the following question, as I said. So we have some path to the root. So this is root, this is x. Now I write here in plus c, in plus 2c, etc. In plus something, d x times c. Then I XOR each number with the corresponding this number, and I want to find the sum. How to do it? First of all, I want to find the total sum on this path. And then I need to find all the fixes. So let's do it. Let's do it. So I want to find a prefix sum. Prefix sum. So let's also initialize that. Prefix sum. Okay, in DFS, here I write that ref of v plus equals a of v. And here I say that ref of 2 plus equals ref of v. And it should be real, of course. Okay, so now I know the prefix sum. Prefix sum of x. And now I only need to fix it for each bit. Yeah, so I need to fix it for each bit. So to do that, let's say I need to say that ans plus equals find fix xc in j and return ans. Okay, now we need to find fix. Actually, here we need ll, not int. Okay, how do we find this fix? So now we only have some fixed bit, like with number b. So we have in plus c, in plus 2c, etc. So how does it work? So first of all, let's eliminate c. How do we eliminate c? So if c is greater than 0, so if c is 1, then it's fine. If c is minus 1, then instead of this, we need to... So, like, if c is minus 1, then we say that c is 1, in is in is this minus 1 minus in and this. Probably like this. Okay, now c is 1. C is simply 1. So we only have x, in, and b. Okay. Oh, what now? Now we have a path which goes up. Okay, so if in is 0, it is kinda easy because we just returned some prepared answer. Okay, what next? So if depth of x is actually less than this number, then actually it's always 0. Okay? Okay, otherwise, if dx oh my god, it's so hard. So its value, like, okay, let's fix, for example, for us to simplify things. For example, 16. So assume that we have here like 3. In this case, we would like to go up till we get to 32. And then it's a very basic answer. Not much time, actually. So we need to go up by like 2 to the power b plus 1 minus initial. This is what we want to do. So if the dx is less than... Ah, this is wrong, actually. This is wrong. So instead of that, I should have written... So actually, I want to assume that now I have... I want to assume that my current number is 0. Okay, basically, so if initial is 0, then I can return prepared prepared for b and x. So I have just a prepared answer. Also, if in is it in if in contains this bit, then I want to return total bx minus find up x x this XOR and b. Okay. And the next thing is, so now it's 0. Okay, now we want to jump up. Actually, we want to jump up. So assume that we have a 0. For example, like here 3. Then we actually want to jump up until we hit 16. So we take to the power b minus minus initial. So go up equals this minus initial. So if go up is at most dx, is greater than dx actually, then we cannot go up and we return 0. Otherwise we return find up x of up x go up 1b b. Actually, I think we've done it. We only need to write the write prepared and total. We need to write prepared and total. We need to write prepared and total. So how to do it? How to do it? Actually, the best way to do it is again with the DFS. Okay, what prepare? Okay, we resize them in the same way as the array jump. And total. What do we do then? Then we want to write prepare DFS function. DFS prepare 0. Okay. So how do we do it? How do we do it? So we have a vertex. We want to find out total of v of like bit and v, and prepare of bit and v. Let's understand how we do it. Yeah. So first of all, to find. Actually, let's assume that. No, let's assume that we need to find it. Okay, to find a total, we simply need to find the total of its parent. Okay, so total for int b 0 b. Okay. So total is total parent and prepared parent. So if it is not its parent, then we can take it from the parent. Okay, and then we say simply the total B is total parent plus what? So if we don't have this bit, then it's +1. If we have this bit, then it's -1. So it's actually this minus what? Minus AV and this and this. Okay, this is total. Okay, actually I want to calculate this fix here and then maybe use it. Great. Now what? So now we want to calculate the function prepared. So prepared B. So how is it calculated? It ignores first 2 to the power B vertices, and then it does not ignore the next 2 to the power B vertices. And after that, it takes everything here as if it was prepared. So so we need to calculate prepared B. So first of all, if the depth of V is at least is at least 2 to the power B plus 1 actually. Then to pre-calculate this, we need to take this so we say here prepared is prepared B jump, and then we need to add here the preparation for this segment. So how do we calculate the preparation for this segment? It's just total of B this jump and minus total of the next jump. Okay, so it's fine. The second case is when this happens and then this is cut somewhere. So else if this is true, then prepared BB is just this total, nothing else. Else prepared is 0. So actually we are finished. So if it just works, then we're happy. Unfortunately, I pretty much doubt that it will work as expected. As usual, we will just see now. Yeah. Okay, it did not work. Okay. Big jump. Let's calculate it. So if b plus 1 equals jump dot size, then it's simply 0. Else it's this thing. And then we just put everywhere big jump. Okay. Not what I was expecting here. So for some reason, find bamboo is pretty much bad. Ah, dx is a failure. Yeah, I should have expected that, because actually I had to write this. Okay, now 16, 13, and 2. Almost there, but still something is off. Okay, I think we'll need to draw this example to see what's going on. Yes, so we have a tree. We have a tree. 2, 3, 6, 5. And we have several queries. So first of them is 1, 4. So 1, 4 is I'm writing here 0, 1, 2, and 3. So I'm basically XORing it, and I'm getting 2, 2, 2, 6. Of course, it should be 14. Okay, what are the fixes? So fix is okay. Actually, maybe this is wrong because it should be 12 instead of 14. Find rootants x c in is 16. Well, this is what's wrong because it shouldn't be 16. It should be 14. And prefix sans? Prefix sans is 16, yes. 11, 14, 16, yes. So for the fix, the fix should be at -2. But the fix wasn't -2 always. Okay, the first fix should be -2. So this should be -2 actually. Okay, it's saying that it is total bx. Hmm. No, it's not fine. Why is total so much incorrect? For example, for v equals 2. V never equaled... I forgot that I have actually a DFS. Yeah. Okay, of course it is probably not correct, but at least we can submit it. I think by the moment it loads, it is already like wrong answer. Wrong answer test 2, I guess. Unfortunately, the probability that it is fine is pretty low. Compilation error. Will there be any errors actually? No? Oh my god, what's... Okay, maybe it's here. Why is there a compilation error? Ah, okay, now it's probably fine. And still it won't accept. Probably. Memory limit exceeded on pretest 2? What? How is it memory limit exceeded? Ah, really? Too many long longs? Well, I can divide needed memory by 2, probably. If we really want it, I can do it. But probably it's still not enough. So this is a bit of shame. Oh no, this time it's wrong answer. Okay. Okay, this was a painful problem. Unfortunately, we didn't solve it. What can you do about this? Hmm. Okay, let's have a quick discussion of all problems. The problem is array divisibility. So array is beautiful subject to an integer k if when you take only the elements whose indices are divisible by k, then the sum of such elements is also a multiple of k. So formally, not formally, but on an example. So what you want here, you want that the sum of all elements is divisible by 1, the sum of even elements is divisible by 2, the sum of each third element is divisible by 3, etc. How to do that? Actually, there is a very simple construction. You just put here 1, here 2, here 3, here 4, here 5, etc. Then the sum of kth, sum of each kth number will be just like k plus 2k plus 3k plus etc. for some number of items here. And it's all obviously divisible by k. Basically, that's it. There can be some other ways to solve this problem, but never mind. Corner twist. You are given two grids, A and B. All values there are 0s, 1s, and 2s. You can take any subrectangle, choose two of the corners, and add one there, modulo 3. And you can choose the other two corners and add 2 modulo 3. You can perform this operation as many times as you want, and you want to finish with an array B. So you're given two arrays A and B, and the question is, can you get B from A? Okay, let's try and solve that problem. Let's try and make the elements equal one by one. For example, let's guarantee that this element is equal to this element. How to do that? If they're already equal, for example, 1 and 1, then you don't have to do anything. However, it might be that here we have an element 2. If here we have an element which is not equal to this one, then we have to add something here. Here we have to add 2. So let's just take any rectangle with this corner and add 2 here, and add 1 here and here. So now we have got what we wanted. Now this rectangle is correct. Now this corner is correct. Now let's take the next element. Again, we would like to make them equal. And again, it's possible that they are not equal. For example, 2 and 0 here. So we want to add 1. However, this time, not all ways of adding 1 to this corner are good. For example, if you take this rectangle, then yes, you can add 1 here. Oh, sorry. Let me redraw it lower. For example, we have two rectangles. Already in this corner we have equal number ones. Here we have 0, here we have 2. We want to fix this 2 so that it becomes 0. However, it's bad to choose, for example, this rectangle, because we can replace this number with 0, but this will replace this number with 0 as well. And we don't want that. We don't want to break the elements which are already fixed. So to fix that, let's just never... So when we fix an element, let us always choose a rectangle in which this element is upper left corner. So always when some element is fixed, we just can touch them, because each next element is fixed by choosing some rectangle in which it is upper left corner. Again, for example, then we fix this, so this is now 0, then we fix this element by something like this, etc, etc. Also, for example, notice that actually we can fix all elements except the last one in this row. So this element, we're unable to fix it, because there is no rectangle in which this is upper left corner. So for now, let's just stop here. Let's start with the second row. Again, we take this cell, and we choose some rectangle in which it is upper left corner. Notice that by doing this, we never spoil the previous row, because it is upper left corner. And again, we can fix this row, then we can fix this row, etc. So actually, we can make this part of the matrix equal in A and B. So everything except this angular thing, it is fine. Now the question is, can we fix this red thing? And the answer is actually the following. If it is already fixed, then we won. Otherwise, it is impossible to fix. Let me explain why is that. Notice that actually this operation that we managed to do, the operation that is given in the statement, it never changes the sum of any row. So for example, if we take this row, which is in the center, none of its elements are really changed, so its sum is preserved. And for this row, we have +1 in some of its cells, and +2 in one of its cells, and +1 in the other cell. So in total we get +3, which is 0.3. Therefore, in this row, the sum is preserved. And likewise, in each column, the sum is preserved. So whatever you do, and however you do, you never change any sums in any rows and columns. So notice that if so the sum of this row is equal to the sum of this initial row in our matrix A, because we can never change the sum. Let me somehow denote it. For example, this, let us call this sum A. Let us call this sum A prime. Let us call this sum B. Okay? And let's call this P because it is purple. And it's same here and here. And also here we have some element, I don't know, C, and here we have D. Okay? C and D. So let us write some equalities. So first of all, we have A. This is the initial sum in this row. We know that it is equal to A prime, which is the final sum in this row. Notice that this A prime is actually purple plus C. Okay? So assume that C is not equal to D. In this case, it is not equal to P plus D. But P plus D is B. So in this chain, we know that A is not equal to B. So if in the end we didn't get the same row here and here, then A was not equal to D. But if A was not equal to D, then actually we, from the beginning, were unable to get matrix B from matrix A. To get matrix B from matrix A, you at least need to preserve the sum in every row. But in this row, from the beginning, the sum was not same as here. This means that since they were different from the beginning, you will never be able to get B from A. And therefore, if this procedure failed to make this row as you wanted, then actually there is no procedure that could do it. Essentially, and likewise, let's put it the other way. If A was equal to B, then actually this procedure should have worked, and it should have transformed this row into this row. Yeah, because if all these elements are correct, and the sum in these two rows is the same, then actually the last elements are also should be equal to each other. So actually there are two cases. Either this procedure Sorry. I only explained for these elements. So if these elements are different in this part, then we understand that it was impossible. In the same manner, you can prove that if any of these elements is wrong, then it was impossible to fix some column, because the sums in these two columns are different. And likewise, if these two elements are different, but everything else is the same, then actually in the last column the sum is different. Or in last row, as you want. So in the last column, if the sum is equal, and all these elements are equal to these elements, then the last elements in these two columns are also equal. Therefore, our procedure should have worked. If they're different, then the sums in the columns are different, and it is impossible. So actually, it's possible to transform A to B if and only if in each row sum A is equal to sum B, and in each column also sum A is equal to sum B. That's it for problem B. Now problem C. Have your cake and eat it too. So we have three arrays, A, B, C, of same length. Also, they have the same sum, which is equal to total, some number. You want to split this array, split this thing into three parts of the same length. So, I mean, in the same, when I say in the same length, I mean that this length L is same here, here, and here. This length K is also same, and this length M is also same. And then you want to somehow make a permutation of these three arrays. So I draw it like this. We choose this, this, and this. But actually you can choose any three parts which are all in different rows and in different columns. For example, it is allowed to take these three parts. And you want each part to be at least total over 3. So this is your problem. So in terms of problem, you want from each of these three arrays choose a segment such that all these segments don't intersect, all these segments cover the whole array, and all these segments, each of them is at least total over 3 separately. This is the problem. So how to solve this problem? Notice that let's now assume that we always take the first segment from the first array, the second segment from the second array, and the third segment from the third array. So let's assume that the order of the segment is known beforehand. Then actually it is a very easy problem. It can be solved greedily, actually for any number of arrays and any number of segments. So you want this sum to be at least total over 3. Let's take the minimum possible segment with this condition. Notice that if you take any more elements, then it is not profitable, because instead of that you could put them in this segment, and it could be better for this segment. So if there is any answer in which in A there are some extra elements, then actually there is also an answer in which A has the minimum possible segment. This follows from the fact that all numbers are non-negative. Since all elements are non-negative, it is always profitable to shrink your array a little bit and give the element that was there but now isn't to the other array, to the other segment. So let's take the minimum possible A, and after that let's take with the same greedy strategy the minimum possible B. And after that, we can uniquely identify what are the elements of C, and we can find their sum and check that they are indeed also at least total over 3. So, again, briefly, using a greedy cycle or something else, find the minimum possible prefix of the array, which will be A. Then, after this place, with the same greedy strategy, find the minimum possible B, and then check that the remaining elements that are in C also have sum at least total over 3. Okay, if this worked, then it is possible. If it didn't work, then it wasn't possible because we couldn't do better. If there is any subdivision into 3 segments, then actually you could shrink this segment A until it was minimum possible, and then you could take this segment B and also shrink it until it was minimum possible. This could only expand the segment C, but since it's still so short, it was short from the beginning. Okay, but what if we failed to choose the correct order of A, B, and C? Well, actually, there are only 3 factorial equals 6 possible orders. So let's just try them all. Let's try all possible 6 orders of our arrays. For each of them, it's just a linear solution. That's it. Okay, problem D. Swap dilemma. So given two arrays of distinct positive integers a and b of length n, we would like to make both the arrays the same. Two arrays x and y of length k are said to be the same when for all i's xi equals yi. Okay, we have two arrays, array A and array B. We can make two simultaneous swap. Ah, actually, I didn't notice. I even didn't notice this solution. This condition. I really didn't notice it. I didn't know that it was there. It's funny. I really didn't know it was there. Okay, actually, I don't know how to solve this problem. I thought that we could do any swaps. It's funny. It's really funny. Actually, I will ask my friends what they think about it. Okay, let me explain what I was doing. So I forgot about this condition. So I only solved the problem when there are two arrays. We can do simultaneous swap. One swap in A and one swap in B. Any type of swap. And answer the question if it's possible to make two arrays the same. Well, first of all, let's sort one of them. and simultaneously sort B. So if sorted A is not equal to sorted B, then this is always impossible. Yeah, because of what the operation of sort preserves, it preserves the multiset of all elements. And all the swaps that are listed in their statement, they also preserve the multiset of swaps. So if you have some operations which preserve the multiset of elements, and you have two arrays which have different multisets of elements, then you cannot get one from the other one, because if you did, in process you had in the process you had to change this multiset, but you weren't able to do it. So to check that two multisets of elements are equal, you can just check instead that the sorted orders of the arrays are same. So if the sorted A is not equal to sorted B, then impossible. Oh, let me just write no. Answer is no. Okay, now let's assume that they are equal. Then actually each swap, you might know that each swap changes the parity of permutation. Let's just assume for now, temporarily, that A has only different elements. Yeah? If A has only different elements, let's renumerate them, rename them, so that these elements are just 1, 2, 3, 4, etc. n. Let's just rename them and pretend that they are from this set. Then A and B are just two permutations. So A is a permutation. It can be written scientifically as A is from symmetric group Sn, and B is also from symmetric group Sn. Then each operation changes parities of A and B. So if initially the parities of A and B were different, then in the end they will also be different. So you cannot do anything about it. So if you don't know what the parity of permutation is, you should Google it, because it is a very important concept from group theory and from competitive programming. Okay. Each operation changes because it's just one transposition. Yeah? Therefore, you need to find the parity of both permutations in the beginning and check if they're same or not. To do that, you can just... there are several known ways to do that. For example, merge sort. Merge sort is able to find out the parity. Also, some segment trees, I believe, can do it, but I am not an expert. Well, that solves the problem when all elements are different. But what if some elements are same? For example, like we have 3, 5, 5, 6, 8, 9 is our sorted array. Let's still make a permutation out of it. So let's still call it as 1, 2, 3, 4, 5, 6 in both arrays. Yeah? So actually, after this, we will have two elements which are the same. We know that they're same, but we gave them different labels. One of them is labeled with number 2, and the other one is labeled with number 3. Let's still do absolutely the same thing. Let's still do some operations with A and B. Okay? So if in the end we have 1, 2, 3, 4, 5, 6, both of them have the same labels, then actually both of them are the same arrays, because 2 and 3 are both numbers 5. Yeah? So maybe some different labels are marked with the same number, but this same number is same in A and B. So actually, after the renumeration, after we remove the labels and take the initial arrays, they will be equal. So the other case is that the parities are different. So we got two permutations and they have different parities. For example, it is even and this is odd. Okay, actually it is not a problem, because what you can do is you can swap two labels of equal elements. So let's, in our head, take two equal elements with two different labels and swap them. This never changes anything in terms of arrays. So still 3 has number 5 and 2 has number 5. But in terms of permutations, this permutation is now odd. So if you have a permutation in which two elements can be treated as equal ones, then you can always switch its parity by swapping these two elements. Yeah, because in terms of elements, you didn't swap them. They were 5 and 5, and they are still 5 and 5. But in terms of labels, you change its permutation, its parity. Okay, therefore, you can, if you have two different elements, you can always make it the same if you have two equal elements. Then you can always make the same parity of both of them. And after that, you can make them equal. Okay, this all works if we ignore this condition. Okay, so what I want to say? I want to say that let me draw a table for you. So there can be correct answer and there can be reported answer. So the correct answer can be yes or no. And reported answer can be yes or no. So reported answer is what I do with all this explained before solution. And correct answer is what they expect in our problem. So yes, yes, it's fine. No, no, it's fine. What is this called? So when correct answer is no, but our answer is yes, which reported, it is called false positive, or the error of the first kind. And this is called false negative and the error of the second kind. Are both of these errors possible in our solution? Actually, no. If our solution said no, then even with the extended set of operations, it is impossible to transform one array into the other one. So if we said no, then the actual answer is no. It cannot be yes. So this cell is impossible. False negative is improbable in our problem. We can only get false positive. Well, actually, for some reason, false positive is also impossible. The actual reasons is that somehow we can always preserve the first array and make any even permutation in the second array. Why is that? I honestly don't know. I honestly don't know. There are some reasons for that. Ah. So I just asked Turmax, he said why it's true. Actually, you always need only r minus l equals q minus p equals 1, and you can just perform a bubble sort. So if you want to make two arrays the same, yeah, how can you do it? Let's just put the minimum in the beginning of the array. Yeah, for example, minimum is somewhere here, and in this array, it's somewhere here. Okay? How can we put the minimum in the beginning? Let's just swap these elements. Okay, let's just swap these elements, then swap these elements, then swap these elements, etc. We do this till the moment when in one of this array the minimum is in the right position. So it's here. But here the minimum in some other position. Now if n equals 2, then from the fact that the parity is the same, it follows that here the minimum should also be here. Because otherwise we have an array like 1, 2. Here we have an array where minimum is not in the first position, then it's in the second position, then it's the 2 is here, and that means that they have different parities. So n equals 2 means that we have already 1, because the minimum should be in the first position. Otherwise, n is at least 3. Then let's take any two elements here and just swap them 2 till we get the m here. So in the upper array, we still move m by 1 position to the left. And in the second position, we just swap 2 random elements. The only thing that we need to preserve is that none of them is the minimum. Okay, now we got that both of them have minimum in the first position. Now let's cut these 2 elements and forget about them. And then, by induction, we sort these 2 arrays. That's it. Actually, you only need swaps of 2 consecutive elements, and that's it. Okay, swap dilemma. Finally, problem E. I love balls. Alice and Bob are playing a game. There are n balls, of which k are special. And they take a random ball. And if you take the regular ball, then the move is swapped to switch to another person. And if it's not, then it's not switched. So if special, then it's preserved and the same person gets the second move. Well, for example, let's assume that these are special and these are not special. First of all, let's forget about these elements. Let's assume that there are no special elements. Okay? Then there are there are k special elements. Let's assume that k for now is equal to 0, and there are only n minus k not special elements. Then we definitely know that the first player gets n minus k over 2 ceiling not special elements, and the second player gets n minus k over 2 floor not special elements. And among all subdivisions of this set into 2 sets of these sizes, all of them are equal probable. Therefore, actually each element has a probability of this, over this, of getting to the first player, and 1 minus this of getting to the second player. These probabilities are not independent. For example, if we know that some element has gone to the first player, conditionally, this increases the probability that all other elements go to the second player. So for each of them, the probability of going to the second player increases, just by a little bit. However, mathematical expectation doesn't care. For mathematical expectation of some of several random variables, it is just additive. It is the sum of independent, or not independent, but separate mathematical expectations. Okay? Therefore, for each element, there is a mathematical expectation equal to AI times this probability. Mathematical expectation of its impact on the first player. It is 0 if it didn't get to this player, and it is AI if it got to this player. So on average, it is this number. And for the second player, it is the other thing. Okay? Moreover, actually, the impact of not special elements on the result is fully defined by the order of these elements. So the only thing that we're interested in is the order of these elements. Now let's return back these k special elements. Let's assume that they now exist. Notice that still all n minus k factorial orders of these elements are equal probable. So actually this impact, this part of this answer, never changes. Always, among these elements, the mathematical expectation of their part to the first player is sum of these numbers, and for the second one is the sum of same but floor instead of ceiling in this fraction numbers. Okay. Now the question is, what is the impact of these elements? Well, since they don't change the order of moves, actually we can consider them also independently. So we can just imagine that k equals 1 and consider this for so each element separately. We consider its impact independently as if k was equal to 1. Because actually, the position of each element of this k is independent of the positions of the others. In terms of... So, okay, let's assume that we have these n minus k elements and they're just nails. So we have nails in the table. The only thing that matters for these k elements, for each of them, is between which two of these k nails, n minus k nails, this one fell. The order between these k elements does not matter at all. Only matters between which two nails it flew. Because of that, we can consider them independently. They don't anyhow affect each other. Moreover, each of these n minus k plus 1 positions for a special element is also equal probable. Yeah, because basically it's just n minus k plus 1 factorial permutations, and there are n minus k factorial permutations for each of these positions. So there are equal number of them wherever we chose to put this element. Okay. So, what is the probability that this special element got to the first player? There are n minus k plus 1 positions, and among them, n minus k plus 1 over 2 ceiling are going to the first player. Therefore, the mathematical expectation of the effect, the impact this element imposes on the first player is AI times n minus k plus 1 over 2 divided by n minus k plus 1. And again, since mathematical expectation is additive, we can sum this among all special elements. Okay, in total, let's denote SP as the sum of special elements and not NSP as not special elements. Then the answer equals the following thing. Special elements for the first player are multiplied by n minus k plus 1 over 2 ceiling divided by n minus k plus 1. Not special elements are multiplied by n minus k over 2 ceiling divided by n minus k. For the second player, the same thing, but floor instead of ceiling. So special elements are multiplied by n minus k plus 1 over 2 floor divided by n minus k plus 1 plus nsp times n minus k over 2 floor divided by n minus k. There is one special case when n equals k. Therefore, there are no not special elements. But if there are no non-special elements, then this is equal to 0. And we can just ignore this at all, so we don't have to divide by 0. Never in this solution. So basically, in the case when n equals k, only these two add-ons matter. Okay, problem G. I didn't solve it, unfortunately. Well, I kinda solved it, but never was able to write the full solution. Problem F I don't know how to solve, so let's ignore it. That concludes my tutorial. Have a nice day.